So today we are going to talk about mechanical damping in MEMS. Actually, before we talk about that, let's talk about something else. Quarter's almost over. So I'd like to talk about mechanical damping in MEMS today. I think I can finish it today, but if we don't finish it today, we'll definitely finish it up on Friday and then start something new. That's something new that I would like to talk about on Friday is just pressure sensors, which is another classical MEMS device. We're going to look at how deflection of membranes and all that kind of stuff works for square and circular membranes, and then talk our way through, capacitive sensing and usually piezo resistive sensing for pressure sensors. Once we finish up pressure sensors, I would like to talk about gyroscopes, which is an interesting device because it takes into account both sensing and actuation on the same device, because you have to induce movement in order to be able to measure the rotation. And then we're at the time where we're supposed to have our final. So we're effectively pretty close to being done with this class. On the syllabus, I had mentioned something about, let's pull it up just for the sake of argument. Dropbox MSE 402 is going to be somewhere down here, I think. Syllabus. This project, which counts for a quarter of your grade, I never wrote an assignment sheet. We never discussed it after the first day. I'm not going to make you guys suffer through trying to figure something like that out within this last week of class. So we need to figure out what is going to happen with the grades. So my suggestion is simply to kill this and then make this 33%. That was the wind, I guess. Okay, because that was very aggressive.
I saw it, I was like, I better say something.
Yeah. So effectively, each of these things would now count for a third of your overall grade instead of a quarter of your grade to compensate. Does anybody have a problem with that? Let's start there.
Where's the other 1%?
33 and a third. 1% for writing your name on the things you submitted or something, You're gonna get way more than that, I'm sure. I just want to make sure that what we're doing sounds reasonable, because we are changing the syllabus and all that kind of good stuff. Yes.
How many homework assignments do you have?
So that's a fantastic question. The short answer is several. I would say at least 4. I just have to get off my butt and write them. So that brings me to my plan for, so what I want to have happen is 1 week from Friday, you guys do the in-class portion of your final exam. And then we have the Monday and Wednesday of the following week, we will be off for Mardi Gras. Then we have the Friday of the following week. So if we look at our calendar here, that's talking specifically the 24th of February. So we have that class meeting. And then we also have a class meeting on the 27th of February. So the 27th of February is when your take-home portion of your exam is going to be due. And since that's also the last day of class, and we talked about this earlier, that's also when your homework assignments that are left are going to be due. So I would like to utilize the class meeting on the 24th and the class meeting on the 27th just to answer questions about homework problems and all that kind of good stuff, so that you guys can get it done and all that kind of jazz. Does that sound like an unreasonable thing to utilize those 2 class periods to answer any questions that you guys might have, so that your homework grade and or your exam 2 grades will be high, so that you're not freaking out about those things impacting your final grade appreciably?
That sounds good. So basically, if we get all our assignments done before the 24th, there's basically no reason to attend class on those days.
That's correct, though. So those 2 days are, I will be here, and anybody who wants to ask me a question related to MEMS is welcome to show up and do it. And that's what those 2 class meetings are about. So I am holding class. I am not canceling them or anything like that. But if you don't, yeah, there's no new material that's going to be covered. Originally, those 2 days were designated, if we look on the thing down here, for the student presentations, which you guys are not giving because I forgot to assign it, and I don't want to make you write me a paper and come up with a 10-minute presentation in a week's time. I think that would be unfair to you. Like, I think you could do it, but you don't need that stress, and I don't need it either.
Yeah.
So we're killing these and replacing it Q&A sessions for anything that you don't understand. So let me see what's going on in the chat here. Will you be having more homework from the latest lectures? Absolutely, yes. So for sure, I want to generate a homework set from electrostatic actuation, piezoelectric actuation, thermal actuation, and magnetic actuation. We kind of jumped around a bit. So like, I actually don't even see mechanical damping on here, but that's what I'm about to talk about. We're going to talk about pressure sensors, and we're going to talk about gyroscopes. So that would be 1, 2, 3, 4, 5, potentially 6 homework sets, but I might combine some topics just so that you don't have so many actual assignments, or I don't know, maybe it would be better for some of your grades if there were a bunch of small assignments, all of them weighted equally. I don't know how you guys feel about that. Like, I don't want to kill you with homework, but I do need to, you know, in some way, shape, or form, measure your competency at looking at those type of systems. So, but the short answer is there should be enough homeworks remaining to where if you didn't do a great job of turning in the first few, you could significantly offset that by doing the remaining ones. I just have to sit down and write them, which is my goal for Friday afternoon. All right, so it sounds like nobody is woefully opposed to the plan. So that's what we're going to do. All right, so let's talk about mechanical damping in MEMS. So I've broken this down into several kind of miniature topics. So the first miniature topic that we are going to talk about is just a refresher on damping. And then we're going to talk about concept of mechanical quality factor. So we talked about damping very briefly when we talked about our accelerometer relationship, and then also when we were talking about mechanical noise. So for a simple harmonic oscillator system, like many of the ones that we deal with, the force is a combination of product of mass and acceleration, which is our classical definition of force. We also have some damping coefficient that represents the mechanical damping in the system, what we're talking about today. This is multiplied by the velocity, giving us some damping force. And then we also have Kx, which we know is Hooke's law as a restorative spring force, right? So our overall force is three different portions of forces. One of those is a damping force. So gamma total here represents the total damping coefficient for our system. Okay. So in a MEMS system, there are multiple different things that can contribute to the overall damping coefficient. Okay. So there is a classical mechanical damping, effectively just meaning that this structure itself, because it is made of a real material, will tend to lose some amount of energy when it vibrates. Then we have things like anchor losses. So effectively, some portion of the vibrational energy will be transmitted into the support structure, which is also another form of mechanical loss. So there's going to be a damping coefficient associated with that. There are what are called surface losses, which we'll talk about later very briefly, but effectively, if our surface is rough, if we have an oxide on it, things like that, that is going to cause some amount of mechanical damping. There are mode conversion losses, where if we have two vibrational modes with a resonant frequency that are close to each other, we can see some amount of losses as energy is transferred between those vibrational modes. And then the most dominant form of damping in a MEMS system is usually air damping, where literally the viscosity of air messes with or causes losses in the vibrational energy of our system. Okay, so we're going to talk about those constituent parts, and then here we're kind of talking about how everything works as a whole. Okay, so damping is defined as the restraining of vibratory motion by the dissipation of energy. Okay. So we just talked about how there are numerous damping mechanisms in MEMS. So when multiple loss mechanisms are present, the damping forces add and the total damping coefficient is simply the sum of the damping coefficient associated with each of the different loss mechanisms. So Y total would be, or excuse me, gamma total would be gamma 1. Why is this not writing? Plus gamma 2 all the way out to some gamma n, where each of those individual gammas represents, again, the damping coefficient for each particular loss mechanism. Okay. Our damping coefficient is measured in Newton seconds per meter. Okay. It is actually relatively uncommon to deal with damping coefficients by themselves. Instead, most engineers talk about mechanical losses in terms of what's known as a quality factor. So, quality factor is often used to represent mechanical losses in a system. Okay. Quality factor is defined as the ratio of the initial stored energy to the energy lost in 1 radian of oscillation for a vibrating system, okay? So from this relationship, we can see that Q and gamma have to be inversely proportional because Q represents stored energy over losses and gamma itself represents losses. So mathematically, we can define our quality factor as omega naught times our mass divided by our damping coefficient. And omega naught times mass is simply the square root of spring constant times mass over our damping coefficient, which is a unitless quantity. So if each individual damping mechanism has its own damping coefficient gamma, each one will also have its own quality factor. So from that, we could say that gamma total will be gamma 1 plus gamma 2 all the way out to gamma sub n, or the square root of k times m over q1 plus the square root of k times m over q2 all the way out to the square root of k times m, not k sub m, over q sub n is the root of k times m times 1 over q1 plus 1 over q2 all the way out to 1 over q sub n. And from here, we can see that gamma total divided by the square root of k times m is the sum of the reciprocals of the individual quality factors, or the inverse of the total quality factor of the system. So this is important because we can see that the quality factors effectively add like capacitors in series. And by that I mean, or resistors in parallel. And by that I mean that if we have one quality factor that is significantly smaller than all of the other quality factors, that is going to be the dominant term. So our overall quality factor for our system will be smaller than the smallest quality factor. So if we have some large loss mechanism, that's going to drive our quality factor down, regardless of how well all the other aspects of our system perform. So I'm mentioning that because we're about to talk about material losses or the intrinsic losses in a system, which can be on the order of have quality factors of like 10 to the 13, like extraordinarily high quality factors, but we rarely actually see those in practice because of other loss mechanisms. Okay. All right, so let's start talking about our different losses that we will experience. The first of which will be material losses. So material losses occur due to movement at the atomic level that results in the generation of heat.
Losses due to phonons.
Yeah, so it's like an internal friction. As the atomic structure of the material vibrates, it heats up because of interactions between the individual molecules that make up the material itself. So this internal friction or these material losses is the intrinsic limit because this is the material acting on itself, creating some form of energy dissipation because it's converting energy into heat with everything else ignored. So this is the best case scenario, right? So the quality factor associated with material losses is the highest number, right? These material losses depend on temperature, the vibrational frequency, so what frequency we are exciting our system at, and the vibrational mode of the structure. So what I mean by vibrational mode of the structure is let's consider that we had, a cantilever beam. Okay, so we would expect to see, I would say 3 vibrational modes for that structure. Bending in the smallest direction, bending in the larger direction, and then extension, right? We can imagine causing the system to vibrate by causing it to shrink and contract and expand, by causing the tip of the beam to displace up and down, or the tip of the beam to displace left and right, depending on the size of things. We could also have a vibrational mode associated with torque as well, right? So those are the different vibrational modes, and our devices respond, or the structures respond differently when each of those vibrational modes is excited. So the material losses that we are going to see effectively depend on how easy or how difficult it is to excite it in a particular mode. Okay, so at room temperature, a simple viscous damping model is appropriate for most MEMS structures. So we are going to simply take our regular stress strain relationship. T is equal to ES, and then we are going to introduce viscosity into our equation. So this is mu gamma. Viscosity, making sure I spell it right, measured in Newton seconds per meter squared. And this viscosity acts on the time derivative of our strain. So in the frequency domain, much like we've done other times, taking the derivative with respect to time is multiplying by a factor of j omega. So this is going to look like ES plus j omega mu gamma times S. So this term here represents elastic damping losses for a particular vibrational mode. Is it okay that I went to the next page, or do I need to go back? Oops, too far. All right, so I don't know how I finally managed to get it to scroll pages instead of jumping to the top of the next page. I'm just gonna not touch anything because I wish it would have been doing that for months. So the quality factor associated with mechanical losses, I'm going to give it subscript QI. We'll talk about why that is in a minute. It's simply the Young's modulus divided by our viscosity multiplied by our vibrational frequency omega. So this is QI because this is commonly called the intrinsic quality factor, which once again represents effectively the highest possible quality factor that could be achieved. Now, something that's fairly interesting here is that E, Young's modulus, is a material property, and viscosity, mu sub gamma, is also a material property, which means the product of our frequency and our quality factor has to be a constant. So this really represents a scaling law for MEMS devices, right? So we could rewrite this expression as F times the intrinsic quality factor will be equal to E over 2 pi times our viscosity, which will be a constant for the material that our vibrating microstructure is made of. Okay, so this FQ product is the figure of merit that's used to determine whether or not you can use a particular material to generate a high quality factor resonator. So hard materials like silicon and diamond have really high FQ products, 10 to the 12 or greater. I want to say one of the largest reported FQ products was for a silicon plate micro resonator, and its FQ product was greater than 10 to the 13. So really, really up there. And then plastic materials and metals, which can deform more easily, tend to have lower FQ products, somewhere in the ballpark of 10 to the 8. Right? So if we want a good resonator, typically speaking, we want a very, very high FQ product.
The higher mineral materials or more metal materials.
Right. Yes, absolutely correct. Yeah, so it gets into elasticity and the ability to not undergo permanent deformation, I think is really what it's coming about from, right? So the next thing that we're going to talk about here is anchor losses. This is going to be a lot of talking and not a whole lot of math. So since microstructures are anchored to a substrate, meaning they don't float effectively, for mechanical support, yeah. Oh, I thought somebody left. Okay, sorry, no, weirded me out. For those of you on Zoom, our door appears to be possessed to some extent. Yeah. It's the ghost of a whole lot of crushed dreams. So Anyway, so since microstructures are anchored to a substrate for mechanical support, when a structure vibrates, some small but non-negligible portion of the vibrational energy is transferred to the support structure or to the support. So these are what we call anchor losses. These anchor losses depend on the location of the support point and the type of anchoring used. So the reason why we're not going to introduce a whole heck of a lot of math here is because analytical analysis is practically impossible to do to determine this. We have to use computer simulations and all that kind of stuff to do this for the most part. For a simple cantilever, there is a closed form solution for the most part, assuming that the length is much longer than the thickness, and that's about the only structure that I was able to find literally any information on. Everything else involves computer simulation, okay? So for a cantilever, which I can spell this, quality factor associated with our anchor loss will be approximately than our thickness. And that's literally the only mathematical, geez Louise, representation that I could find, okay? Now, many occasions, we don't really particularly need a high quality factor. So we don't care a lot about the energy that's transferred into our support system. So for an example, in an accelerometer, anchor losses really aren't that big of a thing. And in actuators, it's not really that big of a thing either. That being said, if we have something that we are trying to utilize as a resonator, we typically want to minimize the anchor losses as much as possible because that's literally wasted energy that isn't getting transferred into the vibrational mode that we're trying to establish. So there are some methods here that are kind of hopefully qualitatively will make sense to understand why they're used to reduce anchor losses without any numerical support. So to minimize anchor losses, in resonators, symmetry is usually exploited. So I'm going to give you guys a couple of examples here of simple structures. So this first one is what's called a tuning fork resonator, okay? And so we have an anchor on both sides. Now, if we had a single beam, we would see that we would experience reasonably high anchor losses for this. So instead, what designers usually do is for the two beams in parallel. So that when the system vibrates, one of the beams deflects up and the other beam deflects downward. What happens in this situation, so let me call this real quick. This is a double-ended tuning fork. So the stresses from the two different resonator arms cancel each other out at the anchor points because they're deflecting in equal but opposite directions. If there is no net stress and strain on the anchor point, there's no energy lost to the anchor point, or the energy lost to the anchor point is significantly minimized. So this is one way that symmetry is used to minimize anchor losses. Another way for a different resonator structure. So this would be a longitudinal mode resonator. So let's say that we have an anchor point up here and an anchor point down here. And so this one is choosing the anchor points at a location to where the net stress should be zero. So if we have a longitudinal mode resonator, so effectively something like a piezo electric resonator, to where we can cause this material to extract and expand in the indicated direction. Well, if we locate our anchor points at the nodal point of the resonator where there is no stress, we get no anchor losses and therefore very high quality factors. So effectively, we electrically excite this system and it's vibrating in and out like so, which is what quartz crystal resonators, how they usually work. And we wind up getting very, very low anchor losses and therefore very, very high quality factors, important for resonators where we're using it as a timer. Okay, so that's another way that it's done. This is a longitudinal mode. Let me write this down. Beam resonator, where the location of the anchor points is what's giving us low anchor losses. And then over here on the right, I'm going to draw one more. And so this is going to be a torsional resonator, and it uses a slightly different strategy. Drew that line too long. So this is kind of similar to that magnetically actuated rotational gimbal that we looked at earlier, but the purpose is significantly different here. Okay, and also we only have a single axis of rotation. I'm just trying to put this in a frame of reference to something that you guys have seen, right? So we have torsional spring here, and the same thing on the other side. We have an outer resonator and an inner resonator. Because the outer resonator literally contains more material, it has a larger mass and therefore a lower resonant frequency. So effectively what happens in this structure, which is a torsional resonator, the inner resonator will resonate at one particular frequency, a high frequency, and the torsional resonator will resonate at a low frequency. And so all of the vibrational energy of the inner resonator effectively gets decoupled to the anchor because of the outer resonator. Okay. So the losses that are experienced are not in the primary vibrational mode. They're in the secondary vibrational mode of the outer resonator. So that's another means by which anchor losses are minimized. Let's talk about surface losses now. We talked about this briefly a little while ago. This discussion is going to be just as brief because there's practically no information on it. Or at least nothing really about quantifying it. So surface roughness. Surface contamination. And the presence of oxide layers, which to my understanding is really just another way of expressing surface roughness, because oxide layers are usually amorphous, so they don't have a nice flat polished surface. Presence of oxide layers.
May mean the difference between intentional surface roughness and surface roughness as a byproduct of the human process.
Yeah. So this can all reduce Q of a structure. So that's literally all the information that the textbook had. I did look into how it's measured. So this is actually kind of interesting. And I think this is also a lot of where the presence of oxide layers comes about. So how surface losses are measured is typically you measure the quality factor of your resonator prior to a heat treatment, and then you measure it after a heat treatment, and then any difference is attributed to surface losses caused by the development of an oxide layer. For most MEMS devices, this is not really problematic because the magnitude of the surface losses is typically small, but as your mass gets smaller and smaller, so your scale gets smaller and smaller, approaching MEMS devices, it becomes very, very problematic. So for you nano guys, this is something you have to worry about. Now we can talk about mode conversion losses. So if we have, so let me practice out. For a resonator, ideally, only a single resonant mode should be excited at a given time. That's going to give us the highest possible quality factor. If the structure has multiple resonant modes, with similar resonant frequencies, some vibrational energy can be transferred to these parasitic modes. So imagine that you were trying to make a resonator out of a cantilever beam. And the thickness of the beam and the height of the beam were of similar dimensions. You would expect the resonant frequency of each of those modes to be close to each other. And if you're transferring energy into one vibrational mode, you can get sympathetic resonance in the other mode. The total quality factor. So we'll see. Is given by 1 over Q total would be A1 over Q1 plus A2 over Q2 all the way out to A sub n over Q sub n for n parasitic modes, where A1, or actually let's call this A sub I, is the fraction of total energy in mode I. Okay. So as a quick example here, let's say that we had a resonator with a quality factor of 100,000 and 99.99%, 99.9%, because that's what I did the math for, of the energy is associated with this first mode. And the quality factor of the second mode is 100, and only 0.1% of the resonator's total energy is associated with that second mode. What we'll find is that the total quality factor is 0.999 over 100,000 plus 0.001 over 100. Take the reciprocal of this thing, and our quality factor reduces down to 50,025 and some change, right? So even though only 1,000th of the total energy is in that parasitic vibrational mode, because the difference in quality factors of those two modes are so large, we see an overall reduction in quality factor of about a half, right? So that is mode conversion loss, right? Now we get to the big problem, right? So usually most of these things are insignificant in scale to the effects of air damping. That's what we're going to talk about now. So viscous losses due to fluid flow, and I'm going to put fluid in quotation marks here because at the scale we're talking about, air is a fluid. Are often the dominant loss mechanism. At the micro scale. Because of this, MEMS devices are often operated at low pressures. So significantly less than 1 atmosphere and very regularly vacuum packaged to mitigate viscous effects. So our textbook has a graph that I like, so I'm going to draw it for you guys here. It's pretty simple and straightforward. And this is quality factor as a function of pressure, and then we'll get a little bit more into the math behind this relationship in a moment. Okay. So on the vertical axis, we have quality factor. On the horizontal axis, we have pressure. And we're going to have something like this, and I'm drawing it in the opposite direction that we're going to look at it, which will make sense in a moment, right? So for very low pressures, we typically observe very high quality limits. And then we have this region here at the moment. And then as our pressure approaches atmospheric pressure, we typically have constant but relatively low quality factors. So we're going to define these regions and explain why we get this behavior. But before we do that, I want to introduce one other little thing here. So in this region of very high pressures, the mean free path of gas molecules is typically much smaller than the critical dimension of our device. So let me write this down. So gamma is the mean free path of a gas molecule or an air molecule. And DC is the critical dimension of the microstructure. And then in this middle region, we have gamma greater than our critical device dimension. And then in this region, our mean free path is much, much greater than our critical device dimension. So what do I mean when I'm saying mean free path? Any of you guys heard of that term before? Any of you mechanical type folks know what mean free path means? Okay, so mean free path is, so mean means literally average here. So it is the average distance traveled between interactions, okay? So for a system like this, what we're meaning is the average distance traveled before we hit a gas molecule, okay? So at high pressures or atmospheric pressure, the mean free path of air is something in the ballpark of like 60 nanometers. So it's very small. Okay, so every 60 nanometers of travel that our microstructure moves, we should expect to, on average, for it to have an interaction with a gas molecule. As our pressure is reduced, that mean free path is going to get longer and longer and longer, right? So the region on the far right is the viscous regime, okay? So in the viscous regime, the mean free path of our air molecules is very small compared to typical device dimensions, and the air acts like a viscous fluid. So instead of having individual interactions with molecules, we're interacting with the fluid as a whole. As we lower our pressure, we get into the molecular region. Our regime. So this is where our device is going to start interacting with individual molecules because our mean free path is on roughly the same scale as our critical dimensions. Before we go on further here, let's talk about critical dimensions. So if we have a microstructure, what do you guys think the critical dimension might be? It's going to depend on the microstructure. So for a microfluidic channel, typically the diameter of the microfluidic channel is the critical dimension. If we had a capacitive accelerometer or something like that, the distance between the plates is our critical device dimension. So it's really the smallest dimension in our system that means something is usually our critical dimension, right? On the very left-hand side, we are operating at extremely low pressures, meaning that our mean free path is very long, and so we are not getting a lot of molecular interactions. This is the intrinsic regime, where effectively air damping is completely negligible. You have a question, Hayden? Or you...
No.
Yeah. Okay. So these are the different regimes that are available. Most MEM structures are operated at pressures in the molecular regime because full vacuum packaging costs a lot of money. So we remove some of the pressure.
You can save that in space. And get the cost of it.
Very much so, yeah.
Just manufacture everything.
Is it like $1 million per kilogram to move it up there or something like that?
Part of that cost comes into reusability, so SpaceX can bring it down, and some of the companies, I think, have both of these space with these technologies to increase the turnover rate. Really, it's just, it costs a lot to make something here and then put it in space.
Yeah.
Like throwing away the airplane after every possible flight.
Yeah. All right, so yeah, it's a yeah. So we are going to look at models for air damping in this regime. And so to do that, we need to have mathematical relationships for things that we're talking about. So our mean free path, gamma, lambda, yep, you're right, lambda, sorry. Lowercase lambda is RT times the square root of 2 times pi times dg squared times NA times P, where let's define some things here. So R is the universal gas constant. It has a value of 8.3145 joules per mole Kelvin. T is just, let me write this, universal gas constant. T is simply temperature. D sub G is the effective diameter of the gas molecule. My handwriting is getting worse. And I also can't spell molecule. For air, this is usually given as 3.65 angstroms. And A is good old Avogadro's number for chemistry class. 6.022 times 10 to the 23 molecules per mole. And P is simply the pressure. And from this relationship, for a fixed temperature, we can easily see that our mean free path and our pressure are inversely proportional to each other. So that as we lower the pressure, our mean free path gets longer. And so at lower pressures, our device will interact with the air molecules less frequently, therefore giving us a lower damping coefficient. Okay. So the ratio of the mean free path to the critical device dimension has a special name. It's called the Knudsen number. This is simply lambda let's call it gamma again, over DC, which is our critical device dimension. And this Knudsen number is used a lot in fluid dynamics. We are going to be talking about the regime where 0.1 is less than our Knudsen number is less than 10. This is the range that most MEMS operate in. KNUDSEN, Knudsen. KNUDSEN number. So with these two quantities, we can now talk about mathematical models for the different types of air damping that we are going to most commonly see in a MEMS device. Okay, so the first one that we're going to talk about is squeeze film damping. So imagine that we have plate. It is movable. And then down here, we have a substrate that is fixed. If we were to apply a force to this plate, it would have some velocity in the down direction. And what squeeze film damping represents is literally the air squeezing out from between the plate and the substrate as the plate travels towards the substrate, right? So there's a couple of things here that we need to consider, okay? So if our velocity is small, we're effectively giving air plenty of time to move out of the way. And so we just have a damping coefficient associated with it. But if our velocity is quick or large, we can compress the air and it's going to behave like a spring because it's going to push back on the plate. And so we'll have some associated spring constant with our squeeze film effect as well. So one way to model squeeze flow, which is what I've described here graphically, is to use the effective viscosity for the gas, okay? So for a narrow gap, like what we would likely see in micro scale devices, the effective viscosity, mu effective, is going to be the viscosity at standard pressure. So it, let me write this here. This is the viscosity in the viscous regime. So we have our viscosity divided by a factor of 1 plus 9.638 times our Knudsen number raised to the 1.159 power. Since our Knudsen number depends on our mean free path and our mean free path depends on pressure, we can say then that our effective viscosity is a pressure dependent quantity, okay? So this is our effective viscosity for a narrow gap. We can quantify squeeze film damping by looking at the squeeze number, So let me write this here real quickly, actually. Effective viscosity. Then we're gonna look at our squeeze number. Sigma, I'm gonna call it sigma SQ because we have so many other sigmas. Squeeze number, mathematically, our squeeze number is 12 times mu effective times W squared. Talk about what W is in a moment. Divided by P times D squared times omega. So W is the width of our plate, where W needs to be less than or equal to the length, so that we have some idea of which dimension to use for a rectangular plate. D is the plate separation distance. And omega is our vibrational frequency. So when our squeeze number is small, this represents air squeezing out without being compressed. Okay. When our squeeze number is large, this represents not giving the system enough time to squeeze air out, and we have compression. Okay. So large squeeze numbers represent the air behaving like a spring. Small squeeze numbers represent the air behaving like effectively a fluid that's getting squished out. Okay. So the damping coefficient for our squeeze film damping is given by 0.42 times the effective viscosity times A squared, where A is our plate area, divided by our gap cubed. Let me write this. A is plate area. And our spring constant, if we're compressing our air, is 0.25 times the effective viscosity squared times A cubed over pressure times distance to the 5th power times omega squared. So this is if we have a solid plate pushing air out from underneath it as it travels towards a substrate, which is exactly what we saw in our area tuned variable capacitors. So when we had electrostatic sensing and actuation, when we had plates moving towards each other, and we'll also see squeeze film damping in a capacitive comb drive when we have longitudinal movement, right? So that when the fingers are moving closer to each other as opposed to moving back and forth with respect to it. So actually, let's stop here because class ends in a minute. So we'll make this much harder by talking about what happens when there are holes in the plate.
Wow.
Yeah.